Cool. So solid to liquid to gas. How does that work? The main thing you have to learn here is the signs are always the same. Enthalpy and entropy always have the same signs. So let's go for fun. We're going solid to liquid and liquid to solid. How is this going to look? When we're going solid to liquid, we're increasing the disorder, right? Think of it in microstates or just places where the particles can go. However you want to think about it, we're increasing the disorder. Now, because we know these are going to be the same signs, just go with delta S. It's just easier. So with delta S, we're moving from solid to liquids. We're increasing the disorder. There's more space for the ions to go, or molecules to go. It's going to be positive, right? So we know delta H is going to be positive. That's it. Now, if we're going liquid to solid, how's that going to look? Well, we're going from water to ice. Ice is a structure, right? There's more order. Entropy doesn't like that, right? So it's going to be negative. And if delta S is negative, delta H has to be negative, right? So this makes, ideally, the phase change is really simple, right? You just look at delta S, use logic, and just picture it. That's the main thing here. All right, so now this equation, delta G, is the most important equation of the unit. You gotta get it down. Delta G is enthalpy minus temperature times entropy. What are we trying to tell here? This equation helps us determine a lot of things, but for now, we'll focus on spontaneous, non-spontaneous, and what happens when it equals 0. So spontaneous, what does that mean? The reaction is progressive, right? The reaction can occur, the reaction is favorable. These are all different ways you would have heard it, but it all means the same thing. The reaction goes. When you think spontaneous, think happens, right? It's happening. It's going, right? When does that happen? When delta G is negative. When delta G is negative, everything has the permission to go. The reaction will happen. It will be spontaneous. What about non-spontaneous? Non-spontaneous is the reaction doesn't happen. It's literally the opposite, right? Delta G is positive. The way it looks here is when delta G is negative and the reaction is happening, it's going to the right. And when delta G is positive, it's going to the left. Reaction doesn't happen, it favors the reactants. But what happens when it equals 0? It's not at equilibrium technically. What's happening is there's the same number of products and the same number of reactants forming. It's like a middle state. That's what we're going to look at here. This is a phase diagram, or a heating curve actually, sorry. And it's a great way to explain it. The way it works is, this is the heating curve of a substance, right? So here is when it's a solid, here's when it's a liquid, and here's when it's a gas. It's showing us how it goes through each phase. This temperature right here is the melting point, right? You're going from solid to liquid. This temperature is the melting point, and thus this temperature, sorry for that, is the boiling point, right? Going from liquid to gas. That's all cool and all, but what's really happening? You're gonna have a lot of times you're gonna have a question, how do I do the math? And the math here is really simple, it's just a lot of steps. First thing you do, anytime that there's a slope, anytime, Q equals MCAT. That's literally it, right? Heat is equal to mass times the specific heat. They'll give you the constant and the change in temperature, right? Melting point minus whatever this temperature is, boiling point times whatever minus whatever this temperature is. That's literally it. Q equals MCAT for this one, and this one. That's all you have to do. You add those values, and you also add two other values. These, delta H of, in this case, vaporization, times the number of moles. And here it's delta H. Oh, this is fusion. I don't know what I'm doing. And this is vaporization. Also times the number of moles, right? When we add all these values up, that's when you get the total heat from it to go to solid to whatever it wants to be. Quick things to know. Normally, this is not on a scale, but normally delta H of vaporization is larger, right? It takes more energy to go from a liquid to a gas. Think why. Back to here, spontaneous, right? For something to go from a liquid to a gas, it needs a lot of entropy, right? What we learned here, right? Liquid to gas, it's harder for it to go and increase entropy. That's why delta H of vaporization is normally longer. So when you see a heating curve and you see, for example, one being longer, then that's how you know that's higher in terms of quantity. Other thing you can see is varying slopes, right? For example, in water, liquid requires more minus heat to become into its phase transition. So it's gonna have a shallower slope, right? Think of a steeper slope, meaning it's getting there quicker. It takes less heat if it has a steeper slope. Let's try right here real quick. So let me use a different color. Let's use red, right? If we have a steeper slope right here, and then we draw the line here, that means it's gonna take less heat to get to the melting point. Less heat to get to the melting point means what? It's easier to melt. So more steep slope means it's easier to melt or easier to boil, however you want to think about it. So yeah, that's that. Now let's look at phase transitions more. That's where it's interesting. Because phase transitions is when delta G is equal to 0. Delta G is equal to 0 at phase transitions. But what is that? Like, I struggle to understand it. What is a phase transition? And why is delta G 0? Why is it in that middle ground where the same number of products and the same number of reactions are formed? That's where we look here. If you want to look at it this way, think of this. This is your liquid. That's your gas, right? So we're over here. So what's happening? You, at a phase transition, so right here, at this point in time, you're having the exact same number of liquids becoming gas and the exact same number of gases becoming liquids. That's what I mean by saying the product and the reactants are occurring at the same time, right? So the number of gases, so the number of gas molecules forming is equal to the number of liquid ones. Is equal to liquid one. I'm not writing all that, but that's the idea. The idea is you're having the same number of solids become liquid, gas, liquids becoming gas, and the same number of gas becoming liquids. That's the idea with a phase transition. That's what's happening, right? And that's also why delta H of vaporization is larger than delta H of fusion, because it takes more energy from substance to go from liquid to gas than solids to liquids. That's the entire logic behind it. So that takes us to this. This is your phase diagram. There's only a few things to know about it. Solid, liquid, gas. What is a line? A line is something that tells you this is where phase transition occurs. So, for example, if I'm going the solid and liquid line, if I this way, so meaning I'm going from liquid to solid, I am freezing. And if I'm going solid to liquid, I'm melting. Right? That's pretty much it. Other than that, all you have to know is up here at a high pressure and high temperature, by the way, there's a supercritical point. They don't really act. They act extremely strange. At that point, you don't have to know much about it. Just it's up there. And then this is what we call a triple point. Triple point, as you can see, phase changes is supposed to be a line. Bam! Every single line intersects at this point. That means it's a triple point. All three substances, all three phases exist at that point, right? For example, for water is a solid, liquid, and gas, all at that point. And that occurs at a specific pressure and temperature. So yeah, that's that. And then this is Clausius Clapeyron. This is important because it shows you delta H, it shows you the relationship of vapor pressure. And vapor pressure is difficult to understand, but if you get it, it's really, really easy. And the way you get vapor pressure is, think about it conceptually. I have, again, same thing here, liquid, and I want to make the liquid gas. Well, if I want to go from a liquid to a gas, and it's in a closed container, a water bottle, then that gas has to push somewhere. It's going to push back on the liquid, right? Because it's a closed container, that's all where it can push. It can only push on the sides and down. Most of the pressure is going to go on the liquid. That's what a vapor pressure means. That's why higher IMFs or stronger IMFs means less vapor pressure. Because if you think about it, if I have hydrogen bonding, right, it takes a lot of energy to break those hydrogen bonds. And then because it takes a lot of energy to break those hydrogen bonds, less of those molecules become gas, and then less of those molecules put pressure. But if I have London dispersion forces, which is really easy, a lot of them break, a lot of them become gas, and then a lot of pressure is put. So that's why IMFs are inversely proportional. to vapor pressure, right? That's why they're inversely proportional, because vapor pressure is literally putting pressure. So how does vapor pressure relate to temperature, right? Clausius Clapeyron tells us they have a exponential relationship, which they do. I guess the simplest way to think about it is, if I have a gas, you have a kettle of water, you're boiling it a bunch. The higher temperature it goes, the more the gas evaporates, right? When you start boiling water, the first 4 minutes, it doesn't really boil. But the last minute, that 5th minute, most of the water evaporates. That's what it's trying to say. It's trying to show in this beginning curve that the reason the slope is so low is because it's showing at increasing the temperature, increasing the temperature, increasing the temperature, increasing the heat, increasing the heat, increasing the heat, but I'm not getting much of a change in vapor pressure because not much is getting evaporated. But the second it hits that point right here, all of the things is going to become gas. The second it escapes this phase transition and becomes a gas, everything is going to become a gas, and that's how you get the exponential rise. That's it.